So if you could remember in the last lecture, we had started studying random processes, and as we discussed there in the last lecture, that some primary information you have already learned about these random processes in your previous course. So we will actually build on that knowledge of your previous course and try to discuss their applications and understand their mathematical framework for their applications in communication systems. So we learned in the last lecture that random process is actually a mapping to a signal for every other outcome from the sample space of a random experiment. And similarly, as we know that random variable is a mapping from the sample space of a random experiment to a real line. Similarly, on the same lines, random process is a mapping onto a time domain function. Hence, you can also relate a random process with a random variable. So if you fix a random process at some time, then it will become a random variable. Okay. And we saw this random variable in the last lecture, where we have fixed time, and time was now 1 over 1000, 1 over 1000. So if you put this value of 0.001 time or 1 over 1000 in example 5.2.1, in this example, t is equal to 1 over 1000, this will become 0.1 f, in other words, it will become 0.2 pi f. So as we have fixed time at 1 over 1000, you can see that your cosine function will be taking the value 0.2 pi times f, where f is a random variable. So now your x of 1 over 1000 is a random variable taking values cosine of 0.2 pi f. So a random process becomes a random variable if you fix time. Now another example is that, let us say my sample space is now from the output of a dice. From this sample space, I take any omega and I define a time domain function. So this will be a random process, because exponentially with a unit step, this is a time domain function. Multiply this with a random variable, multiply with the outcome of the random experiment, this becomes a random process. Now if you take the same random process and you fix time at 1, if I fix time at 1, what is the meaning? That I have put t is equal to 1, this means it will become omega I e minus 1, and u of unit step function is denoted by u minus 1 here. So u minus 1 of 1, unit step function at 1 is 1. This will be just omega I into e minus 1. But we know that omega I can take the values from 1 to 6. So it will be from 1 to 6, e minus 1 to e minus 2, and so on and so forth, going up till 6 e minus 1. Yes, where all these probabilities, where all these values are random variables. Now this becomes a random variable because we have fixed time on a random process. Okay, so it was already a function, but once you have fixed time, it becomes just a mapping onto the real line, and hence it becomes a random variable where we know each of these outcomes will have a probability of 1 over 6. Also shown these functions, this will be 1 e minus 1, 2 e minus 1, 3, and so on and so forth. Another example pretty much used in communications are discrete time random processes, where we have discrete random processes, not continuous random process as you were discussing before. So one example is that, let us say my random variable omega I, or the outcome of the random experiment, is actually a random variable which is a Gaussian random variable going from with 0 mean and 1 variance. So I define my random process as follows, that at the 0 time it is 0, but at any n at time it is equal to the previous value plus the random variable that is drawn from the normal or the Gaussian random distribution, or the normal distribution, or normal, or this omega is a normal random variable. So again we have a random process, but at each time, each nth value, if you just observe value, it will be nothing but a random variable that is either drawn from here or it is summed with the previous summed values. Next concept that we have to understand are the averages, especially the statistical averages. So you all know about mean and average, mean and variance. So we will build on those averages. We will try to have the mean of the random process. Similarly, we will try to see the autocorrelation of the random process. Now, how they can be defined? Now we know that random process actually is a random variable at given time. Now if you take a set of times, you will definitely get a random vector. So you will be defining the averages for the random process via the averages of the random variable. Now we know what were the averages of the random variable. For a random variable, you have a density function, you have a mean, and you have a variance. But we know that if we fix time, random process becomes a random variable. So once it becomes a random variable, it will again have its density function, its mean, and its variance. And we know mean and variance are just numbers representing the mean and variance, but they are still numbers. But now what is the difference here is that these are numbers, but they will be representing the statistics. If you find the mean and the variance of the random variable which is drawn from the random process at some fixed time, so they will represent the mean and the variance of the random variable at that fixed time drawn from the random process. So it might happen that at various values of time, the mean of your random process changes, because it's still this mean value has to be found out at some time. It has to be drawn from some random variable which is drawn from the random process. Then you have to take the average of all those random variables or their variances to get their mean and variance. So it might change with time, or it might not change with time, but in general it will be changing with time. So we say that the mean and variance at this time will be different from mean and variance at this time. Now how can we mathematically define these definitions? So the mean of the random process, yes, it is a deterministic function of time. It becomes a deterministic function. It is no more random, because once you find the mean, all right. So in random variables, if you find the mean, you just get a deterministic number. The mean is 0, the mean is 5, the mean is 10, the mean is 100. But if you take the mean of the process, it becomes a deterministic function. For example, cos 2 pi ft, a pure deterministic mathematical function having no random variables inside it. And for this mean function, deterministic function, if you fix time, you will get the mean at that fixed time or at that instant. So mean of the random process is a function of time. It will be equal to the expectation of the random process at any time or for all t. And this definition holds because if you take any t, you know, xt naught becomes a probability PDF. Xt naught becomes a random variable, and random variable has its PDF, and you are just finding its mean for that fixed t. So you can just extend it for any t, and you will be getting the mean for any t. So you know the expectation at fixed t or the mean at fixed t is nothing but what? It is the random variable itself times its PDF, as we used to find the mean of a random variable. Random variable times its PDF. So these are the various manifestations of the random process. This one, and this one, and this was the mean function, and this is the mean function. So at various times, this gives the mean, which is the mean of the random processes, which constitute various mappings or the various manifestation of the random process with respect to various outcomes of the random experiment. Let us do some examples. Acha. Hi, Siman Jamil Saab, can you hear me?
जी सर.
Acha. Just trying to know, have you done these types of experiments or these type of examples, or in the previous course, to find the mean of a random process? Or you have just seen a random process? Have you found the mean or the variance, or let us say the autocorrelation of a random process in your last course?
सर एंड में एक एग्जांपल की थी सबकी, मतलब कि एक रैंडम वेरिएबल लिया था, वो था रैंडम ऑसिलेटर था, उसकी एक्सपेक्टेड वैल्यू और ऑटो कोरिलेशन फाइंड की थी. बस एक लेक्चर में वो एक एग्जांपल की थी.
अच्छा, एक रैंडम प्रोसेस की ना आपने?
जी की थी, वो रैंडम ऑसिलेटर था.
हाँ,
रैंडम ऑसिलेटर
क्या?
था.
और उसमें आपका रैंडम नंबर क्या था? ऑसिलेटर का फेज रैंडम था?
सर उसमें मैग्नीट्यूड और फेज दोनों रैंडम थे. मैग्नीट्यूड और फेज दोनों रैंडम थे. फेज 0 से 2 पाई पे था जी.
ठीक हो गया, ठीक है, थैंक यू वेरी मच. All right, so this means that we have to go through these examples. Now let us say that we have a random process in example 5.2.2. So in this example, the random variable was a uniform random variable going from 0 to 2 pi. So you know its PDF will be of height of 1 over 2 pi. But the random process was actually this function a cos 2 pi f naught t plus theta. So why this is a random process? Because you have put a random variable inside. Okay, and for every other random variable, you can very well see, or every other outcome of your experiment, random experiment, you will be getting a different function, function with different delays. All right, but this was your random process, and this was your PDF of the random variable that was making the random process, a random process. Now I want to find the mean of my random process. So what is the formula? I will say, first of all, write the random process, which is x. Now random process is now a into this thing times the PDF of the random variable, which is 1 over 2 pi. This is not a new definition. If you could just map it onto your previous course, what was the mean form? Mean formula was x into f of x. But instead of f, if we have some function of x, because random process is a function of a random variable, in other words. All right. So you would say function of x and then its PDF. This is that function of x. Let us say g of x, you can say, which is now a random process now, because you also have time. times its PDF. Now you try to integrate, 1 over 2 pi are just constant, they will go out. Now if you just you take any theta, any shift, but once ever you will integrate cosine over the whole time period, you will always get a 0, because number of positives is equal to number of negatives. All right, so the mean is 0. Yes, this means that you can take any time t, the mean of your random process at any time t will be 0. All right, another definition, very, very important, is autocorrelation. Salman sir, have you studied also autocorrelation in the previous lecture, previous course? Autocorrelation of a random process?
जी sir, की थी.
Or let us try to again understand autocorrelation from this book. So the exact definition of autocorrelation of a random process is actually autocorrelation at 2 times. It will be expectation of the random process taken at 2 times. So if I take it at 2 times, it actually means I am taking its 2 random variables, because once you fix time in a random process, it becomes a random variable. So I'm taking 2 random variables, taking their products and their expectation, and hence I am getting the autocorrelation. Exact definition will be actually this thing. What is expectation of 2 random variables? Product of 2. It is actually the exact product of the 2 random variables, which is actually xt1, xt2. This will be x1, x2 you can write, or you can write xt1, xt2, the same thing. 2 random variables taking the product, and then you multiply with the joint distribution of these 2 random variables. This is the exact definition of the mean of a product of 2 random variables. All right. So you can also write it like this, or if you want to follow the exact definition, this will be definitely right, because you have 2 random variables, you will have 2 differentials, a joint distribution, and the product of the 2 random variables. Let us try to find the autocorrelation of the random process in example 5.2.2, which we just saw. In the example, you had a random process which was just 2 cos 2, but this theta was a random variable, it was uniform random variable, and it could take the values from 0 to 2 pi. Now for the same random process, I want to find the autocorrelation of the random process. So I will say, all right, take the random process and fix some time t1. Take the same random process and fix some other time t2. Take their product and find their expectation. This is the autocorrelation, and you will denote this as Rx, random variable taking 2 times t1 and t2. So you can very well see product of cosine is equal to half of sum of cosine and half of subtraction of the angle part. So if I add these 2 parts, all right, this will become this function. Add the 2 angles. If I subtract the 2 angles, it will become this function. Now I take the mean. Now what will be mean of this thing? Again, you can see very well that you are taking the expectation of a cosine with this random variable. Exact formula will be distribution of this. This is the random process times the distribution of theta, which is 1 over 2 pi into d theta, or the random variable limits from 0 to 2 pi. So you have a full cosine function. For any value of theta, you are just integrating the cosine over its time period. This will be definitely equal to 0. All right. But for this, very important thing, this is expectation of this, but there is no random variable inside. Expectation is integral with respect to the random variable, but there is no random. This function will just come outside the expectation operator. This is just e of half, and half is again a constant. E of half is just of half. So this total factor will come out, and then this will be your autocorrelation. And as he has repeated, I told you this will be equal to 0. The second term will go 0. The next example is how to find the autocorrelation of example this. In this example, the random variable was a random variable taken from a uniform distribution going from -1 to +1. Some of the steps I found they were missing, so I made my notes there that you can easily understand. So I try to find the autocorrelation. Formula is simple: E of random process at T1, random process at T2. All right, and the random process was actually equal to the uniform random variable. Random process was a uniform random variable. All right, the uniform random variable was taking the values from -1 to +1. So at T1 you will still get some random variable. At T2 you will get again some value of the random variable. This you can say x into x. Both will be some values of your random variable. This is a random variable, is also a random variable. This becomes e of x square, and e of x square is again, this is a function. The functions times the PDF of the uniform random variable, where the uniform random variable, it goes from -1 to +1, so its height will be 1/2, its PDF will be 1/2. So 1/2, this becomes 1/2 goes out, x square becomes x cube over 3 by the integration. Limits, this will become like this: 3 to the 6 to 1/3. So autocorrelation comes out to be 1/3. Same thing is here, but the steps were missing, and you can get the notes, so you can also understand it easily. The next are the wide sense stationary processes. So I think you have also studied this thing. Roll number 144. Have you studied wide sense stationary processes?
Yes, sir.
All right. Thank you. इसमें how many examples you did in the class for wide sense stationary processes?
सर वही एग्जांपल की थी रैंडम ऑसिलेटर वाले जो वो बता रहा था.
अच्छा, चलें.
उसी को स्टडी किया इसमें भी.
अच्छा, ठीक हो. Thank you. All right. So coming back to the lecture, what is a wide sense stationary process? So we have just seen that random process at fixed time becomes a random variable, and random variable will have a mean, variance, PDF, but it will depend on the time at which you have fixed the random process. But many times it happens the properties of the random variable, for example the mean or the variance, they remain independent of time. So depending on what properties are independent of time, different types or notions of stationarity, means constant, station, remain same, can be defined. There are various stationary processes, but we will be just concentrating on the one of the most useful notions of stationarity, and that is wide sense stationary. And in wide sense stationary, a random process, is wide sense stationary if and only if its mean remains constant for all time. So if you find mean at any time, it comes out to be the same value, 444 or 000. It does not change with time. So this mean property remains independent of time. And second property is that its autocorrelation does not depend on the choice of the time origin. The autocorrelation will just depend on the time difference. For example, let us say I'm getting as a wireless signal, which is a random signal, and I find its autocorrelation. Let us say I find its autocorrelation today. I take one value at 11 o'clock. Let us say 11:15 at the start of the lecture. I take another value at 11:40. All right, and then I take the product and take its expectation. If I repeat the same process at 11:15, 11:40 sample, let us say tomorrow or day after tomorrow, and I again use expectation of the product, the answers will be the same, because for if the process is WSS, the autocorrelation will only depend on the time difference of the two samples that have been taken to find the autocorrelation. So the property mean is independent of t. It remains constant for all t. Second thing, that the autocorrelation depends on the difference t1, t2. So here the book defines tau as t1 minus t2, the first time minus the second time. You will follow this notation throughout the course. So White's and stationary, you can also say, instead of this long term, you can also say stationary processes. So stationary, White's and stationary are the same thing, and their mean is just a number because it is always independent of time. But this is a function of the difference of the two times. That is why difference is tau is denoted as tau. Let us see some examples. We saw the example, 5.2.2 earlier, and we just found its autocorrelation, which comes out to be like this thing. You can see the autocorrelation depends only on t1 minus t2, the difference of time. But this is a stationary process. Now example 5.2.2. So we have again xt, but we form a new yt, but we make sure that now this yt is theta, which was a uniform random variable, is uniform between 0 to 2 pi. Instead of 0 to 2 pi in that example, it is only uniform between 0 to pi. All right. Let us find its mean. So, the mean will be the PDF of this theta, which is 1 over pi, because now it is uniform from 0 to pi. It will be 1 over pi. A to वैसी बाहर आ गया cos of this thing. But now you can see this integral will not be 0. Why? Because you are not integrating over the whole time period of cos. You are integrating over half of the time period of cos. It will not be 0. You might be integrating over the positive or the negative value. You won't get a 0. For 0, you have to integrate for the whole period. All right. 1 pi goes out. Cos integral, is sine. Limit 0 to pi. And sine of 2 pi of t plus pi. So you shift sine by pi. All right. So let us say I am studying at 90. I shift by pi. Unit will always become negative. Shifting by sine by pi becomes, or you can say sine alpha plus pi is equal to minus sine alpha, because sine alpha sine pi will be minus sine alpha, and cos alpha sine pi will be 0. Second term goes away, so it will be always minus sine 2 pi f naught t for pi. With 0, minus 0, 0, it is again, minus 2 pi. So adding up, this comes out to be minus 2 into sine 2 pi f naught t. So this is your mean. Here you can see the mean is dependent on t. So this means this is not a stationary process, because the mean has to be constant, but here the mean is a deterministic function. And you can also see Rx T1 T2 is equal to Rx T2 T1. Yes, very simple. Because what is Rx T1 T2? Rx T1 T2 is equal to E expectation of X T1 multiplied by X T2. So again, this will be expectation of X T2 into X T1. So it is the same product. Product is commutative. Same thing. And if the process is stationary, then T1 minus T2 is equal to tau. And this is equal to minus tau. So in that case, if the process is stationary, then we can always say that Rx tau is equal to Rx minus tau. That is, if Rx tau is equal to Rx minus tau, this means that Rx is an even function with respect to tau. because you take tau 4 and tau minus 4, they're the same values. Real function. For example, we say Fourier transform of the real functions, real time domain function, its Fourier transform is conjugate symmetric. Its magnitude is even. As you can see here, the autocorrelation is even. As the magnitude was even and the phase was odd, so you can just check that the autocorrelation function for a WSS or a stationary process is even. Cyclostationary is not in our course, so you can just take it out. This is for master level, so we won't be studying this. Next thing is multiple random process. My question is, why do we have to study this multiple random process? Why don't just, and you can see also in the course it is not specifically mentioned, but without studying this, you won't be able to understand this multiplicity of random processes and why you have to take many random processes at the same time. So that is why this has to be covered. Now, why do we have to deal with these two or more or multiple random processes? Many times, for example, let us say I have a random process coming from a wireless signal, or let us say coming from electronics. I have a low magnitude signal and a lot of noise, which is a random process. Voltage and current, they are randomly moving. So I have a random process, signal is random, and I pass my signal to an LTI system. So I will be getting an output which will be also random. So how my one random is related to the second random? How the second random is related to itself in terms of its autocorrelation? See? So you just pass it through you have just passed a random process through a simple LTI system, which could be a capacitor, RLC circuit, pass band, any simple LTI system. I'm not passing it through a diode or no, I'm just passing through a simple LTI system, and again you are getting a random process. So you have to connect the two random processes at the input and the output and their various autocorrelations. So that is why discussion of multiple random processes arise. So you say is the output of this was the input to a random to a LTI function. Now what is the output? Output will be the convolution of this random process with the simple impulse response of your LTI, and you can see the convolution of a process, because this is not, in convolution you are just integrating, flipping, and then you are summing over time. This WI is always there, it won't be taken out, so the output will also be a random process. But we will be also seeing its proof in detail with just a simple logical conclusion or thumbs rule. So for every omega I, we know we have a different signal, but at the same time our output will also be different, because for every omega I your x t omega is different deterministic function time domain, hence its output will be different. Now, if we have two random processes, how can I define their independence? So if I sample them at these times, all right, x and these are the sampling times of y, I get two random vectors. If the random vectors are independent, then this means that the random processes are also independent. If these random vectors are uncorrelated, then we can very well see that the random variables will be uncorrelated. I think you all of know what is independence and what is correlated and uncorrelated functions. Ani, where is roll number 101? Ani, 101, can you hear me? Last time we absent you. Her paper was very good, that is why I was asking. 101, can you hear me? All right. किससे पूछे? अच्छा हाँ जी हमजा CR of section D 172 roll number, can you hear me? 172. अच्छा आज तो नहीं उनका इंटरनेट खराब हो गया. I have especially using optical fiber so that we don't have this problem for communication. किससे पूछें? अच्छा भाई हाँ जी सलमान जबीर साहब, कैन यू हियर मी?
जी सर.
अच्छा I was just wanted to know, have you studied the meaning of independence? Two random variables are independent and when two random variables are uncorrelated.
जी सर, इंडिपेंडेंस में तो ये होता है कि मतलब कि अगर जिनकी जॉइंट डिस्ट्रीब्यूशन है वो प्रोडक्ट होती है उनकी इंडिविजुअल डिस्ट्रीब्यूशंस का. तो फॉर इंस्टेंस fxy इज इक्वल टू fx into fy, और या इस तरह भी कह सकते हैं कि प्रोडक्ट ऑफ.
ठीक है. और कोरिलेटेड को कैसे डिफाइन करेंगे, अनकोरिलेटेड रैंडम वेरिएबल्स को?
सर कोरिलेशन में मेरे ख्याल में ये होता था कि जो प्रोडक्ट ऑफ एक्सपेक्टेशन है, अगर वो एक्सपेक्टेशन ऑफ प्रोडक्ट इज इक्वल टू प्रोडक्ट ऑफ एक्सपेक्टेशन, अगर ये कंडीशन हो तो इसका मतलब है कि वो अनकोरिलेटेड होते हैं.
E of xy is equal to E of x times E of y
into E of y, तो वो अनकोरिलेटेड है. और अगर ये नहीं है तो फिर वो कोरिलेटेड है.
सही. ऑलराइट, गुड. So actually the difference of these two things, this EXY and EXEY is actually called the covariance. So if the covariance is 0, this means that they are uncorrelated. But if the covariance is, there is some value of covariance, this means that they are not uncorrelated, because the difference is not 0 and hence EXY is not equal to EX times EY. I think also you have studied covariance in your previous course.
जी सर, पढ़ी हुई है.
सही है,
पढ़ी हुई है.
इस बुक में भी दिया हुआ है, आप लोग उसको थोड़ा देख भी सकते हैं. ठीक है. So here we are just talking about that they are independent. This means that they are joint distributions if they are equal, as yours Salman said. So joint distribution of so many random variables equal to the individual distribution of this and this, so then it will be independent. Similarly, for uncorrelatedness, you have to show that in terms of vectors. But again, you don't have to confuse. You won't be going into vectors here. Become very difficult at this level. This will be for masters, just to give you an idea. But this is an important topic, that again, if I know that random variables are independent, then this means they are uncorrelated. Because once I say that distribution is equal to, as your Salman said, that joint is equal to product of individual, then what is expectation? Expectation, you also have joint distributions. E of xy will be xy into joint xy. But if they are independent, then you can very well see ex and ey, they are separated. So if independence is a more powerful property, if they are independent, then definitely they will be uncorrelated. But in general, if they are uncorrelated, then it will not imply independence. It only implies independence, or there is a two-way relationship only and only for one type of random variable, and that is the Gaussian random variable, and hence this is the only property for the Gaussian processes, which we'll be studying in a while. Gaussian processes. So Gaussian processes are those processes that when you sample them, you get a Gaussian random variable. Cross correlation. So auto is same. Cross means two different random variables and you are taking the autocorrelation but at different times. But you are not taking auto, this is cross. But same thing which happens in auto, that you take 2 times. Here you take 2 times for 2 different random variables. It becomes a cross. And you can again see Rx by T1 will be R by X T1, because this, what is Rx by T1 T2? It will be E of X T1 times X Y T2. So this will be, if you just interchange time, you can also interchange this thing. This will be again E of y t2 x t1, which is the same thing here. So they are same. Now, two random processes will be jointly WSS or jointly stationary if both are individually stationary, as well as their cross correlation. They should be individually White and stationary, as well as their cross correlation should only depend on the difference tau. So this means that if I have a jointly random process, then in that case, you know, T1, T2 is equal to tau, and this is equal to minus tau. General definition is already there. All right. So I can say Rx by tau is equal to R by X minus tau. All right. So he says that I have two random processes xt, yt that are also jointly stationary. The meaning of jointly stationary is that individually they were stationary, but their joint, you know, cross correlation is also dependent on the time difference tau. So he says with this information, determine the autocorrelation of the process. Of some process z of t, which is sum of these two random variables, these two random processes. So all right, I want to find the autocorrelation of z of t, where I know I want to show, you know, z of t is yes, z of t, I want to show, you know, that it is also, you know, White and stationary. So I just find its autocorrelation. You can also write T1, T2 here. Book is using, you know, T plus tau, tau, so the difference again tau. You can just write tau also if you already know that it is stationary, but better is that you write T1, T2, but you can also write this thing as given in the book. So this will be T plus tau and this will be T. I put the value of zt plus tau, which will be xt plus tau, rt plus tau, zt will be x and x. Now I take the products. So x will go with this. This will be autocorrelation of tau, because the difference between this and this is tau. This will go with this. This will be, you know, cross correlation of rxy. Difference will be tau, because they are also joint stationary. This with this, you know, it will be y with tau, ry with tau. And what will be this thing? This will be actually ryx of tau, but I can write ryx of tau as rxy of minus tau. Okay, because ryx of minus tau is equal to rxy of tau. So here I can write ryx of tau as equal to rxy of minus tau. Same thing. All right. So if you put here plus tau, this will become definitely minus tau, because this will again the difference. Only the difference has been altered. So this is minus, will be plus. This is plus. This will be minus. This will be minus. Now we have seen the, you know, random processes and multiple random processes, but now you want to relate these multiple random processes with respect to an LTI system. So yes, random process passes to an LTI, output is also random process. But how can we relate the statistics of the two random processes? So we say xt is a stationary random process. It passes to an LTI system. And this pulse response, we say it is also real impulse response. Okay, simple real numbers, impulse response, continuous variable. And the output process, you know, it is convolution of x of t into h of t, is shown in figure 5.16. This is the random process. Random impulse response output is also a random process. Random process goes to an impulse response. Output is also a random. We want to answer these questions. Will the output be stationary? What will be the joint stationary properties of the input and the output? What is the mean in the autocorrelation of the output process? What is the cross correlation between input and output process? Let's try to answer them. So a process is, a stationary process enters. It is a mean of mx. Let us say its autocorrelation is already known. The stationary process, that depends on tau. It passes through an LTI system with its pulse response h of t. So we will see after proofs that the mean of the output will be equal to this. It will be the mean of the input signal times the sum of the impulse response. The cross correlation between input and output will be given as follows. It will be the impulses, the convolution of the input, autocorrelation of the autocorrelation of the input, convolve with the impulse response, flipped over the tau axis. While the autocorrelation of the output can also be given in terms of the input convolve with the impulse response of the LTI system. So first we do this proof. The mean of the output, will be E of yt, will be E of, what is y of t? We know y of t is actually the convolution of the random process with the impulse response, x of tau h of t minus tau d of tau, right? I take expectation inside, so this is a deterministic number. This will come outside the expectation operator. Integration is just linear function. The expectation can go inside the linear function, but expectation will actually hone around x of tau, because we saw that x of tau is a White's stationary process. So when you fix time to the random variables, expectation will not let it pass through. It will be E of x of tau. But we know what is E of x of tau. It is a random process. We are finding its mean. Its mean will be equal to whatever the mean of that signal is. So mean becomes like this, and this is constant. This comes outside. Inside you just have the shifted impulse response, and you're taking its integral. So this gives you the mean of the output. So mean has been found. Second thing is the cross correlation between output and input. So I put the input, I put the output different time. Output is the convolution. I take expectation inside the integral. These two are random variables, so they will go inside the expectation. This is just a deterministic number. This will come out of the expectation. Expectation of the same function, this becomes the autocorrelation of x t1 minus s, because it is a stationary process. Input was stationary or White's stationary. So this becomes autocorrelation T1 minus S, right? I use some substitution. U is equal to S minus T2. So this becomes minus U. This becomes autocorrelation. I change the variables. This becomes minus of U, and you know S is replaced by U plus T2, so minus S minus T minus T2 minus U. T1 minus T2 is our tau minus U H of minus U. So what is this thing? This is actually the convolution of H of minus tau with R X of tau. So convolution is giving you alright. So this is convolution, so I can write it like this. So you can see that the cross correlation depends on the autocorrelation of the input convolved with the the flipped version of your impulse response. Next thing is to find the autocorrelation of the output. So again, output is here. So XY with E, they will become cross correlation S minus T2. This remains the same. I change the variables. This comes out to be like this. This becomes tau. And again, you can see this will be RXY of tau convolved with so you can see here. And we already know that Rx of tau is equal to Rx tau H minus tau. So this comes out to be the formula for the autocorrelation of the output. And you can see here, output is also stationary because it depends only on tau. These examples I am not covering because you don't have to understand them. Now comes the PSD of stationary processes. So we have studied a random process, its mean, its autocorrelation, its cross correlation, it's passing through an LTI system and all that. Now what is the spectrum or the spectral characteristics of a random process? What are the type of signals that are present? So you can see here that random processes contains many time varying signals. If they are slow, then the spectrum will contain low frequencies, or its power will be at low frequencies. Once the signal of the random process are of high frequencies, the power will be mostly around high frequency components. Otherwise, it will be mostly low frequency. So what is the function that we can use to find the power of the various signals in the random process? That is called power spectral density, or the power spectrum of the random process. This is a very useful function which gives us the distribution of the power. So we try to find this power spectral density, and it gives the strength of the power at a given frequency, and its units are watts per hertz. So very important theorem is the Wiener-Khinchin theorem, which says that Fourier of the autocorrelation function gives us the PSD, or the power spectral density of your random process. Calculation is not in the course, but we just have to see that Fourier of the autocorrelation gives us the PSD. Now we found this autocorrelation for one example. Now we have to find its PSD, power spectral density. So you know cosine. Oh, just I've done it now so that students they are revised again. So I have to just find its PDF. So what is its PDF? It is just the Fourier of its autocorrelation. First of all, just for revision, we know if your signal is impulse, then your Fourier is 1. So we know that, let us say if we have an impulse function, then the Fourier will be a constant function. Similarly, if I shift my impulse, we know I get this thing. Similarly, we know that for if we have a DC, so if we have delta F, only a DC impulse, I get a DC signal in time. This impulse in frequency gives you DC signal in time, and you can very well see delta F gives you 1. If I multiply this with EJ 2 pi ft, so I am modulating it. This means the spectrum will shift to F0, positive frequency. Here the function will shift to. But if you do plus, it will shift to. It will map up to minus J2 pi F0 t. So EJ this and E minus is F, and we can just see now cos is EJ plus EJ over 2, each EJ will give you this. This will be your 1 over 2 makes it 1 over 4. This will be your PSD of your random process. आज जी आप लोगों ने PSD भी पढ़ा था पिछले कोर्स में, हैं जी सलमान साहब? पावर स्पेक्ट्रल डेंसिटी
सर बस सर ने यही बताया था कि जो पीएसडी है वो ऑटो कोरिलेशन की फोरियर ट्रांसफॉर्म होती है, ये बताया था, लेकिन मेरा नहीं ख्याल कि एग्जांपल वगैरह की थी।
अच्छा एग्जांपल्स वगैरह नहीं की थी?
मेरा मुझे नहीं एग्जैक्ट पता, मैंने वो लेक्चर एंड में से नहीं लिया था, शायद करवाइए, मुझे पता नहीं।
अच्छा चलो ठीक है। ऑलराइट, सो वी हैव दिस थिंग आल्सो। ठीक है, ऑलराइट, द लेक्चर इज, इफ समवन हैज एनी क्वेश्चन ही कैन आस्क। ऑलराइट, So I will stop the recording.